In a nonlinear system, the output depends not only on the first power of input but also on the higher and lower powers of input parameters. Interestingly, scientists observed that many physical systems at higher amplitudes translate into nonlinear systems. In this video, we shall look at a simple nonlinear system, that is, the double pendulum. Double pendulum is a system in which two pendula are arranged such that the pivot of one pendulum is attached to the free end of the other. Because of this arrangement, they oscillate in the same plane. The upper pendulum and the lower pendulum influence each other while oscillating and produce these wonderful patterns. A simple pendulum is also a nonlinear system, but the major difference between these two systems is the non-periodic motion of the double pendulum. A simple pendulum, even at higher amplitudes, exhibits periodic motion. A double pendulum doesn't repeat its pattern. Another important characteristic of the double pendulum is its sensitivity to initial conditions. A double pendulum has 6 parameters. Any slight change in any of these parameters induces huge differences in its trajectory.
Till now we have seen different aspects and patterns of double pendulum. Now we will try to mathematically solve this system. The important mathematical tool that we use to solve this system is Lagrangian mechanics. In Newtonian mechanics, we have to consider the position components, velocity components and force components of the system. Whereas the Lagrangian mechanics makes it simple. In Lagrangian mechanics, we go after the energies of this system.
There is not a big difference. One can say that it is an elegant formulation of Newtonian mechanics, but to other higher areas of theoretical physics, it takes us smoothly. Lagrangian formulation is more useful, simple to do and more elegant, because symmetries are taken care of in Lagrangian formulation naturally, whereas in Newtonian mechanics one has to take some trouble to put in symmetries.
In Lagrangian mechanics, in the start, we define a parameter known as Lagrangian, which is equal to kinetic energy of the system minus potential energy of the system. Here we can see the xy, x2, y2 are different coordinate components for the two masses. And if we try to find the kinetic energy of the system, what we get is the transition kinetic energy and the rotatory kinetic energy of the system. And the only potential energy of the system, that is gravitational kinetic energy, will give us this simple formula. So what we have got here is known as the Lagrangian parameter for this system. The next step is to introduce Euler-Lagrangian differential. Euler-Lagrangian differential, we obtain two equations. The unfortunate part is we can't integrate these differential equations because they are too complex, and we can't obtain a formula to find the thetas of these particular components. So what we do is we use the powerful Rangaputa method to solve these differential equations on computer to obtain the path of the double pendulum system.
We have seen different aspects of the double pendulum. Now what happens if we add another pendulum? Basically what we are doing is increasing the number of variables in the system and making it even more chaotic. Such chaotic systems, which need not necessarily be related to physics, are studied in chaos theory.
Double pendulum is one example which is pedagogical, because we study pendulums a lot. It's a nice example to start your basic physics education, and it nicely, so this simple example of simple pendulum takes us to this chaotic region just by adding another pendulum. So my PhD was in nonlinear dynamics itself, which is quite a general field, and chaos is a part of that. Simple example of this divergence of trajectories is, let's say our monsoon when it rains. If it rains on a drop falls on Western Ghat, it goes to Bengal Sea. And if it falls in conquered region, it goes to Arabian Sea. So their fate is decided by just few meters where it falls. So that is the example of sensitive dependence on initial condition. But in this case, it is only along one reach of Western Ghat. But if it happens at every point of the phase space, then we call that system as chaotic.
In simple terms, chaos theory deals with systems which have many influential parameters, and the systems are very sensitive to changes in these parameters. For chaotic systems, the approximate present does not determine the approximate future. If you've been listening, we do not use the word random to describe the chaotic motion of the double pendulum. A chaotic system is still predictable if we knew the initial conditions perfectly. A random system is by definition unpredictable even in theory. If a person looks at the stock market graphs, he finds everything random at the first time, but a stock analyst can figure out many things. Chaos theory isn't something to be exploited for application. It doesn't represent some mathematical or scientific discovery that can be used in novel ways. Instead, it represents a set of techniques for analyzing dynamical systems that are deterministic, ranging from analyzing stock market and finance, building neural networks in biology, predicting the weather, population dynamics, digital communications, etc. Consequently, advances in understanding certain classes of these systems lead to advances in understanding the physical world or designing technology that interfaces with such systems.